Yeah, thank you very much for this kind introduction. It's for me a very honor to be the last speaker in this symposium. The title is "What Can a Robot Learn from Humans?" And I think here it's time really to go down to earth and to study what really can be learned. Learning is something which could be done. We can observe that with humans. I think Giulio gave very impressive some examples. What can be learned, what are the failures, what are the success of learning. But the problem is how a machine can learn. And the question is, can it learn itself? Can it learn by other robots? Can it learn by humans? And how to teach that? My roots started at the beginning with first robot. It was a Puma 500. We started to program that. Also looking for the code, then starting to program it very close to the machine. This was very cumbersome. I did learn from tool machining that there is a language APT, which is wonderful if you read the books. But then how to make a robot doing that. Describing objects, describing trajectories, describing actions. Later, we continued developing some languages. We started with Algol-like languages to program robots. Pascal came later. It was a very structured programming language with discipline. You had to structure the program and to define all libraries necessary for that. And later, this was too cumbersome for us. We started to develop planners, geometric planners for assembly operation, for collision avoidance, and developed, we call that implicit programming, a complete autonomous robot system with planners, very heavy planners. But we did show that this is possible to make a robot system autonomous in case the environment is relatively structured. So now if we want to look to other areas, we use this here to show simple things which happens if we have humans and robots sharing the space. One situation that there is a person showing the robot what to do, maybe saying some words. Actually, we have here no spoken commands in this movie. I will later say something to this problem, why this is so complicated to use language and speech to communicate with robots. Okay, but here it's, you see, the robot is explained to do something, how to manipulate the objects, what to do. The robot observes, learns, confirms that it understands what to do. And then after interaction and communication, the robot starts to do something. This is a simple scenario, but in the following you will see that it's really a hard way to do that in a stable way. So looking closer for learning, some examples, what is learning? People can learn how to drive a bicycle, making some experiments. You can learn how to play poker or to play chess, how to throw a basketball. We can learn to solve differential equations. I can learn a poem, studying the text and then reproducing that. And then we have this hell of robots where we need skills, where we need trajectories, where we need interactions, where we need forces, where we need have to look to the environment, and then how learning can be done in this way. This is really the task. So two parts can be different. One is the robot is on its own. We call it unsupervised learning, exploring the world, making experience, looking what happens if I do something, and then to generate from that some conclusions, closing a control loop, and starting to work. There's a lot of work in AI on learning by experiments, learning by observation, where I think some unsupervised approaches have been tested. The other one is to use a lot of training data, to collect a lot of data, and then try to cluster what is important, derive that, and generate one example. Reinforcement learning is trying something, using some criteria to evaluate how good is the task. The other one is learning from demonstration. And who gives the demonstration? One is, of course, the best solution to have a human teacher demonstrating a task, observing that, taking a trace, and then use this information from the external teacher and to generate the internal representation, maybe to imitate at the first part, but the second one is to generalize that so that also some variations are possible, to do something different or something which seems to be similar. So it's a kind of supervised learning, and it's also possible that a robot learns from another robot. We heard also talks that maybe a robot can learn from the cloud, that a lot of knowledge is somewhere in a network. We have observers, sensors taking the data, and I think Alex Zielinski gave some examples that in such a cloud we can have immense information, maybe also skills and other things which can be accessed by the robot. So this is learning from demonstration. So the question is how this learning, maybe motor knowledge, maybe skills like grasping, we heard a lot of talks, can be derived, how to use multi-sensors, and how to generate that. And I think the best solution is what has also been discussed, put the human into the loop, to cooperate, to interact, to make the robot rich, and to tune the machine to do something. To do that, I think it's necessary, if there is a human demonstrator, to observe the human, to understand the body, to represent motion, interaction, to recognize intention. What does this mean, what the demonstrator is doing? And the other one is to generate trajectories, motor knowledge, which sensors to use, generating control loops. I think the child, what Giulio said, has the advantage that it starts very early and is able to try again and again. Every one of us did fall before learning walking, I think about 1,500 times to be able to walk and to do something useful and to move around. So important is to understand how humans do that, how the body works, to have good models, that's one part. And on the other side, to look to the sense of human, which is haptics, which is vision. We understand speech, we can localize. So it's a rich sensor equipment humans have, and to model them and to have some analogy in machines and how to use that, and if it's not available, maybe to take advantage from the human teacher to do that. So we call that area now modeling humans. We call that anthropomatics. And there is Anthropos, automation and robotics inside. And at the KIT, we clustered these different areas. One part is to model this human man-machine interaction, image understanding, speech understanding, theoretical approach to learning in this field. Biosignal processing is important if you couple the robot, and then what is cognition, how to model that, how to use that, and to take information for the robot, for example. And then on the other side, it's important to build robots. We learn a lot how robots work by building new systems, looking to the mechatronics, to materials, everything what has been said. And this is something maybe I have in common with Gerd Hirzinger, that we saw it's very important to build the system, to understand the system, to build controls, and to make them working. So some areas of applications at KIT are medical, micro, industrial robots, swarm robots. So we study not for all areas how to learn, but in all robot groups you can see the problem. How to program them, how to make them doing something useful, how to interact with humans. So at a glance, anthropomatics comprises these areas, looking for the interaction of humans with machines. On the other side, looking to robot technologies, industrial robots, space robotics we never have done in Karlsruhe, so it's a good complementary activity between these our locations and to go forward. Looking back, in the 80s, we started to build completely autonomous systems, omnidirectional with mechanism wheels, having two Puma 260, a lot of vision systems. At that time we had no laser, so we used sonar. And what was possible in a manufacturing environment, to go to a place, to dock at a place, to take work pieces, driving to another station, doing some assemblies, and then to do it completely planned and in an autonomous way without interaction and intervention. This was in the late 80s. Also, the first multi-finger systems have been developed. It was 3 joints, 3 fingers, and we had 4 fingers, and then it continued to today's systems. Here, one study on an arm with 7 degrees of freedom, studying how to map from humans manipulation to a 7 degrees of freedom arm. It was a very rigid arm. And then building the first 2-arm system, which had some analogy to humans. It was a Tammy Masfur designing this machine, combining it with a mobile platform and starting. From there, we studied programming, learning, trajectory planning, all these parts with these machines. Technology evolved. And actually, there are 2 humanoid systems. It's ARMA 3A and B. They work in a concrete environment. They work in a kitchen. This is our benchmark to do defined work. And this machine, which is very close to be finished. So actually the feet and the upper legs have to be assembled as a humanoid robot. So the work to be done for that is, if you looking to the materials, to the mechatronic parts, as we have seen in the last day. Sorry, going back. To have electronics, embedded systems, algorithms, sensors to generate representation internally. And then on the other side, the question how to teach these systems. This is the crucial part. Idea was to demonstrate, to observe, and to map it on the machine, using knowledge about about human motion, or about the human body. And everyone knows it's not possible to map it directly from the human body to the machine. This is an approximative process, so that it seems that the robot is doing similar things like the robot. Okay, then applications, speech, gesture, mimics, the multimodal interface has to be understood, gesture, pointing gestures, etc. And then the hand is identified as a very critical point. One from the mechatronic part, where we had developed various generations of hands with hydraulics, with pneumatics, with electric motors, trying to make them better and better, more adaptive, and more similar to the human grasping point. Here, this is one demonstration where the robot interacts. Here we have accelerated the speed with time 4. You see it's still today very slow to interact with the robot, to make them working in the kitchen like humans. Even children can open the fridge, taking out something more easy than humans are doing that. So this is, for example, one example, a benchmark in the kitchen, loading the dishwasher, deloading the dishwasher, making the dish, and everything is done with a control loop. It has been demonstrated, mapped, and then to make the robot to do it. Here's one example where the question is, what is this? This is a spoken dialogue, this is a book, but the robot is not able to read the book. It's a book on control theory. And so you can ask, what is this? The robot says, this is a book, but you don't know what is inside. So this is some of the problems where semantics are necessary to understand what to do with this and maybe for what it's useful for. Okay, here are these applications using the hands, recognizing this is a kitchen without markers, without anything. It's a natural one, and the attempt was to do that and interacting with humans. So it's not so catastrophic as Giulio said at the beginning of his talk with the sketch where the interaction was a catastrophe. Okay, then some examples of coupled interaction. Pouring is something which is studied also by a lot of other groups. Handling objects with two hands, so it's loosely coupled, or also handling of objects which are rigid coupled. And to do it in a reasonable way, everything is done online with planners, RRTs, or variation of RRTs, which allows finding the right grasp, coordinating the arms, and avoiding obstacles. So then here we have a grasping, pre-grasping, so the robot has to estimate, is it possible to grasp it, maybe it has to move it, and then to be able to do something with this. This seems very simple, but if you look in terms of learning to understand the principle behind, then you see that this is a crucial part to make it and to generalize it to the robot. These are some examples. You can also study doing something with the surface like cleaning and following the surface and to use sensors, haptics, and to integrate that. Okay, how this works. There are various planners with models taking data from sensors, shaping the data, and then generating a lot of grasps. Some people say the robot is dreaming by night. This means the simulator computes all possible grasps, selecting the best one, generalizing that, and then they can be used online. And then when execution, it's necessary, where's the right arm, where is the left arm, are there obstacles, no collision, coordinating that with the environment. Or if the robot cooperates with humans together, this has to be also observed. So here is one interaction with humans where forces have to be detected, and where a human is cooperating with the robot, moving one object, but it's also possible to interact with machines. In this sense, taking it on the hand, taking on both hands, maybe dancing, as we have seen, to move the machine. The robot must know the intention, must follow maybe tactics, the tactile and the force interaction it observes. It's not yet a tango, but it's to show the principle how this could be done. Now maybe some work to how to instruct the robot. One is to observe the robot with the sensors. I will show you that, and to have some mathematical representation. The big lack is that from the language side, the dialogue is very poor from my point of view. I think it's very good we explain people with spoken speech, explain something, make an example, and then other humans understand and can do it. Another situation is, for example, if I ask another person, help me, then very quickly the other persons understand how to help, maybe to grasp something, or the stair to help to pass the stairs. But if you say to a robot, help, this is a hell. To explain what to help, a big dialogue is necessary, how to support. And I think there is a big area where activities are necessary. I think Greg Hager said something that the vision community, he said, where's the state? And I asked him, where is semantics? And he said, 10 years, 20 years from now. And I think this is necessary if we speak on speech, on spoken speech, on explanation. In some papers of the 90s, I mentioned that demonstration is important and comments. Till today, we have some comments, but it's very poor if you say what we can explain a robot using speech. Okay, the principle is shown here. Human shows something, maybe pouring, doing an assembly, disassembly, handling some materials. This is observed by cameras. And then this is mapped to the robot, for example, a two-arm system here with multi-finger hands, and to imitate that or to learn it and to use it. Learning in the classical way from AI, where we started from, is to learn something like operators. Maybe grasp, maybe move, maybe lift, maybe assemble. And to generate from observation these we call operators, people who know strips. They know that there are macro operators that you can build from single tasks, complex tasks. And this, I think, is well understood how to do that with sensors, using also motor knowledge from robots or from observed from the human. What can you do with that? If you give a task and you learn these operators, you can use a planner, giving a task, and then a plan is generated. This works, but it's assumed that it's a closed world, and not an open, noisy, not completely observable world. So something is missing in this area, and it's necessary to look closer to the motor knowledge and to the sensors and the uncertainties which have to be explained. This is something magic. How this is solved and how this can be used. One part in the machine learning is imitation. Imitation learning to observe isolated motion, task, to map them in the memory, to analyze it, then to generate a program and to repeat it, looking similar, maybe like a human is that. I think there are a lot of good algorithms actually available. We are dreaming that a robot looks how to walk, and that ARMA 4, the walkie, that the full humanoid can imitate that. But I think some dynamics are necessary, otherwise this fails, and I think Usama gave some examples how difficult this could be. Another part is learning of how to plan. This means to acquire planning knowledge, so that something like strategies can learn, which allows the robot to deal with exceptions, with uncertainties, how to use the sensors in this situation, not in an unsupervised way, but together with humans. And this is learning planning models. I very shortly explain what is behind that. Otherwise, okay, you can come to courses to Karlsruhe and to listen how to do it. So this is the cycle of learning. At the left side is the human demonstrating something. You see the data gloves. We use cameras. We use markers, different techniques to observe what humans are doing. Then having a trace of images and of trajectories, of action sequences. And then, yes, this is a technique how observation could be done. It's an old image taken from the lab. You see a lot of cameras observing the humans, maybe special cameras for observing the hands. At that time there was no Kinect available doing that at low price and a certain accuracy. What you see here is Swiss Ranger generating a model of the human, a simplified one, but it tracks with 15 frames per second, and it allows to see if the person walking, sitting down, shaking hands, or doing something like that. And these are the sources how the robot is seeing what this person is doing. Internally, we generate representation like that, maybe the objects. This is a test bed, we call it Cranfield benchmark. It's used all over the world to evaluate programming, coding, testing, and how to make it running. Okay, the results you see here are abstract representation, which can be generalized, and then you compile it. It's not a typical compiler one-to-one. It must adapt the actions to the physical target system and then generate a so-called flexible program doing that. Here you see another situation that two persons are doing something. So there's also possible to have a trace, maybe to acquire also spoken signals that one person say, bring me this, and then the robot observes what is happening after the word, bring me a bottle. And this can the robot learn, and then maybe hearing later, if a person say, bring me the bottle, looking to the robot can start to bring the bottle because it has seen how this could be done. This can be generated, it's a little bit difficult to generate the plan. Generates a type of grasp, but a type of graph with arcs and with nodes. And in the nodes are some decision-making processes, maybe supported by humans, by human input, or supported by observations or by sensors or exception handling. And this seems that this is a very flexible method to represent. Here you see some examples. For here at the left side, there's a pouring example, the internal representation in the computer, and then the mapping on a machine. Here you see a sketch how this is presented. Here you see the trajectories, you see the velocities. You can also have other relations observed. And then taking this data, if it's to segment it, to generate a meaningful, useful sequence of actions, which is parameterized. This is important. So the result may be something like this. A sequence of actions of nodes and arcs in a graph. Maybe there are, it's also possible to have some parallel action. It's also possible to have loops. If this is an activity where cyclic tasks have to be performed. And then this is a representation which can be translated to a robot. Important is maybe what is doing the left hand, what is doing the right hand. This depends where the robot is, where are the objects. There is some local decision necessary to decide this. Okay, this shows now some experiments we have done. These are two arms, lightweight arms with 7 degrees of freedom. And this is a study we had done together with the DLR in a common project, where we study how to plan and how to execute that, also using hands which have been developed at DLR. So this is the principle, what happens internally. The nodes, maybe to have some parameters, then there is an action. The result of an action, maybe there are constraints which have to be fulfilled. Maybe there are uncertainties which requires observation, expectation, what happens, what may happen, so that the sensor system know what to observe, when to observe, and how to interpret. This information is necessary. And then you can get such a graph. Here it's, for example, if you grasp a cup, and in the cup is something, then you must hold it in some way, you must know how the gravity field is, etc., and etc. Maybe internally you have a representation like that, representing the constraints, for example, for pouring, what is necessary to do that. And then if you have that, you can generalize that and can apply that to different pouring applications. Of course, the result here is then to have a strategy graph like that, which is a type of program which can be learned. If there are some nodes where there are too much uncertainties, maybe the robot asks for advice, maybe to have some help, or to get a better demonstration to be able to execute that. This is possible today, but it's still cumbersome to implement such a system in this way. So this was a short overview on learning. What I can say is be careful with when we speak with learning. It's a question about what we are speaking, what a robot can learn, what are the capabilities, what are the constraints. Even if we have the big robot cloud in the background, which can be accessed, at the end, the mechatronic system, the sensor system, must work, and the representation must be mapped directly on that. So I come to the end of my talk. Then, Gerd, I want to thank you very much. Congratulations for your work. I hope we will cooperate all in the future and realize some of the dreams together, and also for your contribution to robotics. Thank you very much.